Hello, welcome back to another episode in CSC 263, Database Management Systems at Adelphi University. In the previous couple of videos, we looked at the relational model and we figured out how to capture data using relations and attributes and tuples. What we're trying to do today is figure out how we can organize that data in such a way that we minimize data redundancy. Redundancy is in general considered, under most circumstances, undesirable because it leads to update anomalies. Specifically, if I keep the same information more than once, I have to make sure that when it comes time to update that information, I'm updating it in all locations in which I keep it. And before you know it, data is going to be out of sync, and data that is unsynchronized means that you don't know which one, for example, is the authoritative data. The process that we use to organize data in a way that we minimize redundancy to the extent possible is called normalization. And normalization is chapter 14 in the textbook that we are using. So, as I mentioned before, we want to use a database management system to obtain persistence. And in the case of the relational database, many of the design decisions that we make are meant to further the ability to ensure data integrity, which means that the data that's in our database is correct. And that means that, for example, our integrity rules that we talked about, domain integrity, entity integrity, foreign referential integrity, and the general constraints can play a role in that. The other thing that can play a role in that is the mechanism that we use to organize the data. And that, in this case, is called normalization. It's a structured process, so we can actually write it down step by step and then execute that process as we go through it. And in the end, we may transform some of our relations a little bit, but we only do that to remove redundancy. We do that in a way that we don't lose data, though. So we want to call that process is called lossless decomposition. We do this in stages, and even though an experienced database designer can probably design a database that is almost immediately fully normalized, we can recognize each of these stages, and at least for the purpose of instruction, we're going to not skip any steps, and we're going to make sure that we start at the beginning and go stepwise until we reach our desired state of normalization. That process I mentioned before that we use to take a relation and analyze it and maybe split it into smaller relations is called decomposition. We look at the data and specifically at the meaning of the data in the relation. So for example, look at the example here on the screen. Let's say that I have a relation called grades, and in it I maintain a student ID, a student name, a course ID, a course name, a term, and a grade. So for example, in this case, student ID number 1, last name could be Smith. For course ID 263, which is Database Management Systems, in the fall of 2020, that student received a A-. Our primary key here is the combination of student ID, course ID, and term. It is a composite primary key, and we've chosen this one because it allows us to post a grade for a student in a particular term. In one of the previous videos, we used the combination of student ID and course ID as the key. But then we realized that by doing that, we could only post one grade ever to a student, which means that you potentially could not retake a student. Or if you updated someone's grade, it would lose the history of the previous attempts. Neither one of those are desirable situations. So by adding the term in which a student takes a class, or at least is awarded a grade, to the grades table, we can now recognize that a student can take a class in a term, but only once. And that makes sense because you can't be enrolled in the same class multiple times at the same time. It also allows me to maintain a history of grades, yet each grade can be immediately brought back to the student and the course. We can look at the most recent term. So this is a good way to identify the key. And so the composite primary key again is student ID, course ID, and term. Now we could split this up. For example, we could create a table called grades where we just say this student ID, that course ID, and that term, they got a grade. And then we'll create two supporting tables, one with students and one with courses, to keep the details about the student and the courses. Of course, if I would stop there, I would have lost information. I have not decomposed properly. So what I do want to say is also foreign key relationships. So I want to make sure that when I go from the student ID field in the grades table, that I can only put a student ID in there if that student ID also exists in the students table. So we define a foreign key with the source being grades.studentID and the destination being students.studentID. Similarly for the course ID, I only want to be able to award grades that for courses that exist. So I define a foreign key from grades.courseID, and it has to point to courses.courseID. The referential integrity rule then says if I put a value in course ID, then that value must be present in the courses.courseID field, and if it's not, I can't put it there. So this is a good decomposition. But the question is, why did we do this? Why did we decompose this relation this particular way? That's what the normalization process can answer for us. Another concept that we need to introduce is that of functional dependencies. It is a semantic concept. You cannot deduce a functional dependency by just looking at the database. You have to know something about the data it represents in the real world. A determinant is one component of the functional relationship. A dependent is the other. The determinant in a database table is an attribute that can be used to determine the values assigned to other attributes in the same row. So very abstract. But when I go back, for example, to the previous slide, let me do that. I see that in the grades table, if I see the student ID, I can also figure out what the student name is. So in this case, the student ID is a determinant for the student name. Not the other way around. If I have a student name, I don't necessarily know what their ID number is. I could have two students with the same name. Same thing with courses. I could have a course ID, say CSC263, and with that I also know that I have a course name, Database Management Systems. But there's another course called Database Management Systems, that is CSC565, that's the graduate course, but that means that the other way around is not a determinant. If I have a course name, I do not unambiguously know what course ID goes with it. So that is the concept of a determinant. It exists within a relation though. A determinant, or I should say a functional dependency, exists within a single relation. It does not cross relations. And typically we say just so A points to B. So A determines B, or B is the dependent of A. And it is important to recognize that you cannot do this by looking just at the data. This is something that you have to reason about the actual domain that you're trying to analyze. But with those concepts in place, with the concept of decomposition, lossless decomposition, and functional dependencies, we can start looking at the normalization process, which is meant to eliminate unnecessary redundancy in a database. We'll do that in the next video.